Okay, I welcome you all, and we have been working on commutation relations in a couple of lectures, and today we will continue our discussion, and we would like to see some more commutation relations between, say, linear momentum, angular momentum, uh, and the components of angular momentum. These will be some of the important targets we'll be talking about. And in visualizing angular momentum, in fact, yesterday I talked about angular momentum, and I started with a very imaginal story where I had two characters. The first character was Classica, and another character was Quanta. The character that I had, the Classica knows everything about the classical laws of physics, and on the other hand, we have Quanta, and Quanta is very much experienced about the laws of quantum mechanics. But the two things are quite clear here, that for Classica things are beautiful, there is symmetry and there is continuity. And when we talk about the angular momentum in the framework of Classica, the angular momentum is continuously changing. It has continuous values, and there is a complete dependence of components of angular momenta, say along x, y, and z. But that's not the case when we talk about the quanta. The quanta is, when I look at quanta, when I tell quanta, come on, tell me who you are, it looks very weird, and it follows a different set of rules. It tells me that, come on, you will not find me continuously. You will find me in packets. You will find me quantized. Okay? So this is how we try to differ the two regimes, the regime of Classica and the regime of Quanta. Now I want to take on this story in the framework of angular momentum, and I want to make a better insight so that we can have more interest, we can develop some kind of feeling that what we have been doing is actually connected to the real world. And to execute that kind of thing, if I assume that there is a black hole, and I think everybody knows what a black hole is, even if you are not a science student, you will at least have some knowledge about the black hole. And what we say, that black hole is an infinitely dense object, and the center of this Milky Way galaxy is filled with black holes, and there is a very huge black hole at the center of this galaxy. Now, what am I trying to tell you is that I have these characters, okay? I have Classica with me, and it's holding a key. It's holding a key of say, for example, it's holding a key Lx. Now we understand what Lx is. Lx is a component of angular momentum along x-axis. And I am holding another key. I'm also a character in it. I'm holding a key of Ly. And there is another character. This character is Quanta. And Quanta is holding Lz. So what we have Classica, we have Quanta. Now, Classica is very short because it understands universe only through the classical laws of physics. For Classica, everything is complete. For Classica, every object is a complete mechanical machine. For Classica, you can exactly predict the future. You can exactly know the future if you know the initial conditions. But for Quanta, we have a dilemma. We have a dilemma of dual nature. We have a dilemma of uncertainty principle. We have a dilemma of superposition. We can have a particle at many places at one point of time. So now what is happening? We three people, okay, we are the three characters, Classica, myself, and Quanta. We reach at the event horizon of a black hole. Okay, all of you know what event horizon is. Event horizon is the space around the black hole which cannot be crossed by any of the particles. Even light particle cannot escape this event horizon of a black hole. Okay, every black hole has a event horizon. Okay, now when we go close to this black hole, what we see is, we see that there are three regions. There are 3 points, there are 3 dots. And somebody is telling us, if you want to see what's inside, you have to use the keys that you are holding. Okay? You have to use the keys. And we are the 3 characters. Classica, myself, and the Quanta. Classica is having Lx with him, me having Ly, and Quanta having Lz. Now what happens? The Classica goes and uses his key. He is holding a key of Lx. And he's very sure, he's very confident about the outcome. Okay, so what he does, he holds the key, he opens, and he finds a flash of light. And he uses it 2 times, he finds a flash of light. What does it mean mathematically now? It means that with, am I talking about Classica or Quanta? Classica. I'm talking about Classica. Are you getting my point? So what he is doing? He is trying to see what is inside the black hole. He opens it and he finds a flash of light. And he again opens it and he finds a flash of light. But what he is holding? He is holding the X component. He is holding the X component. But this black hole, for Quanta, the Classica is not the right thing. Quanta realizes that Classica will not be successful. He will not see everything that he is sure of seeing. Getting my point? So what is happening here? If Classica is opening the hole, opening a magical position 2 times, he gets a clear result. What does it mean? It means that the X component of angular momentum must be, they must commute. If you obtain a commutation relation between Lx and Lx, it will come out to be 0. Now what is happening? Now Classica again goes, opens. Now I tell Quanta, go and open it. He goes and opens it. He finds an explosion. Are you getting my point? Now the story reverses. Now Quanta does the job first and Classica does the job now. But what is in the mind of Classica? He feels that he will get the same result as he got when he used his component 2 times. Lx, Lx. But when he opens, he finds a completely new thing. He finds a completely new thing. So what does it mean? It means now Quanta tells Classica, hey man, it doesn't work. Your black hole is quantum mechanical. It doesn't work. The order is very important. If we will change the order of opening that spot, the results will not be only different, the results will give you something extraordinary. Something that's not there. What am I trying to tell you is, when Classica acts as Lx, Quanta acts as Ly, I'm with them. Lz, what they see is they see me as the outcome of that experiment. So what I say Lx and Ly does not commute. And in case of Lx and Lx, there is a commutation. So this is how it works. So what we say is, even a black hole, see, when we demonstrate the black hole, we demonstrate it through general theory of relativity. And general theory of relativity is an extension of classical physics. Are you getting my point? But if you want to know anything about this black hole, you cannot be sure of that. You will have the results that will differ. The order will make the difference. The things are weird. You will not be sure of everything inside a black hole. So our target is to go with this angular momentum algebra. I think you must be already aware about these things, but yet we will go with it. Suppose I take a commutation between Lx and Lx. Right? Now let's go with it. Lx and Lx. So what this is Lx cap minus Lx cap and Lx cap. All right? And yesterday I have calculated, I have shown you what Lx is. Okay? So what is Lx? Lx is minus IH bar times y dou by dou z minus z dou by dou y. This is your angular momentum operator. And you rightly remember angular momentum? R cross P, okay? You have a determinant, and from solving that determinant will lead us to the x component of angular momentum. It will lead us to y component of angular momentum and the z component of angular momentum. Now for the time being, we need only what? We need the x component of angular momentum. So what we would like to do is, we would like to calculate this commutation. So how can we calculate? We would like to act it on some state function. Say that state function is psi. Say that state function is psi. Right? So what's going to happen? Come on. So you will have minus IH cross will be common. So I will write minus IH bar outside. Isn't it? And inside I will have Lx. And what is Lx? That is y dou by dou z minus z dou by dou y. Okay, would it be only minus IH bar or the square of it? It should be square of it. Isn't it? Because you will have it two times here. So here and here. Again, you will be writing what? Y dou by dou z minus z dou by dou y. So this is my Lx cap. This is again my Lx cap. And then I have minus. Again the same thing. Y dou by dou z minus z dou by dou y. And y dou by dou z minus z dou by dou y. But you are acting this all on psi. So everywhere you will have psi. You will have psi here, 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 and here, and here, and here. And when you will solve it, you will exactly find the terms that will cancel with each other. Okay? And when they will cancel, you will get the result equal to 0. Okay? So you can do this algebra. And we would like to do the same kind of algebra when we will take Lx and Ly. So you will do it yourself, okay? So you will find, what you will find? You will find they commute. You will find LX, they commute, LY, they commute, LZ, and LZ, they also commute, and the result is 0. Right? This is one thing. Now let's go with another thing. Say I have position X and LX. Right? I want to find the commutation between X cap and LX cap. This one will be, okay, what will be? I will put a psi on it. I will get X cap, LX cap minus LX cap and X cap, and I will execute this on the wave function side. Right? Okay, now let's go with this. So what will I write? I will have X times minus IH bar times Y dou by dou Z minus Z dou by dou Y. Minus, now this thing first. So I think I would like to get this minus IH bar out. I don't want to create the confusion. Let me have it out for all. So minus IH bar is out, okay? So now this Y will be first. Y dou by dou Z minus Z dou by dou Y, and then X of psi, and here you will have X of psi, here you will only have psi. This is what it will look like, right? Okay, so what's going to happen here? I have minus IH bar out. Now, okay, so this will remain as is. X times Y will give me XY, and then you will have dou psi by dou Z, right? Minus, okay, this X will multiply with Z, so you will get XZ, dou psi by dou Y. Okay, that's fine. Let me make a small bracket for it. This is gone. And now we want this part. You can see it. We want this part. Now for this part, what's going to happen? This X and psi will remain here. This X and psi will remain here. All right? So let's solve it. So what's going to happen? So you will keep this thing, a track on. We would like to evaluate this part. What you will have here. See, the first thing that you have is minus. I will keep that minus outside. And then you will have Y dou by dou Z of X psi. Y dou by dou Z of X psi. This will be one thing. Minus Z dou by dou Y minus Z dou by dou Y of X psi. Are you following me? Huh? I have put those terms there, the first two terms, okay? I'm looking for the other terms here. Now here you can see you have a UV rule, okay? So minus is outside. So minus is outside. So Y is okay, it is there with them. So X as X, derivative of psi will give me dou psi by dou Z plus psi as X, the derivative of X, that is dou X by dou X. Am I right? Can I close it? Okay, so this part I have evaluated. Now I have this part. You see, minus is outside. I may commit a mistake. I don't know, I'm not sure, but let's hope I don't. And if I commit something, you can stop me at that point of time. So here I will put minus. Now Z is here, okay? Okay, Z is here, and I will put a bracket here. So X has X dou psi by dou Y plus psi as X dou X by dou Y. Isn't it? Right? Now, directly I can see this term, you can see the derivative of x with respect to x, isn't it? So this will go. All right. Okay. And here, where am I? Okay, here it's fine. So this is dou psi by this. Now here, see this term. Look at this term. It is a partial derivative. And you understand partial derivative. Partial derivative means if you have a partial derivative of y with respect to x, the x will act as a constant for y. Right? That's why you have partial derivatives. So here you have dou x by dou y. So x will act as a constant. So this term will immediately be equal to 0. Isn't it? So this thing is gone. This thing is gone. Okay, anything else? Okay, now let us look back. So this thing has existed, okay? Now you see, what is here? Look at this. Yx dou psi by dou z. Come on. Yx dou psi by dou z. This is positive and that is negative. So this term and this term is gone. Am I right? Okay. Now another term that we have here, what is that? Okay. Zx dou psi by dou y. Zx dou psi by dou y. Can you see it? So this is minus, that will become plus because you have a minus outside the brackets. So this term is also gone. Isn't it? So what we are left with? We're left with psi, and it's all multiplied by what? Minus IH bar. Am I right?
Just dou x by dou z.
Yeah, where? This.
Second.
This.
Dou z.
This is dou.
Dou x by dou z.
Are you sure? Then this will be 0. Then this will be 0. That's right. You have got it correct. Absolutely correct. So everything is gone in it, I think, huh? So the commutation between x and Lx has led us to minus IH bar into 0. This is equal to 0. So they commute. You can exactly measure the position and the x component of angular momentum. Now let us go with another exercise. Okay? Which exercise? So for this, y Ly is equal to z Lz is equal to 0. This is gone. But let's go with the other part of it. Now what's that? Now let me choose the commutation between x and Ly. Okay? Let's take on the commutation between x and Ly. So what you are going to do here? So you will have the same story. X Ly minus Lyx. And you will operate this on the eigenfunction side. And then finally you will remove this side once you have resolved it. Okay? So what you'll have x. Now I have Ly. The outside I will have minus IH bar. I want to get that out. So here you will have z dou by dou x minus x dou by dou z minus z dou by dou x minus x dou by dou z multiplied by x. Okay? But this whole thing is multiplied by the eigenfunction psi, isn't it? So let me resolve the first two terms here. The first two terms will be what? xz dou psi by dou x. This will be the first term. Okay? The next thing, minus x squared dou psi by dou z. right? And you better know that we are starting from this minus IH bar. Okay, now this part is resolved, and after this part you have what? You have a minus. Okay, so I will take on the next page. Can I take it on the next page? Come on. So what I have here? I have here minus. Okay, then yeah, what was it? It is Z. It's Z dou by dou x minus x dou by dou z, but it will have x psi multiplied. It will also have x psi multiplied. So you will be looking for that UV rule. Okay? So what you will get here? Come on. So z is out. Here x will be as its dou psi by dou x plus psi as its dou
X by X, that's one.
dou x
By X.
by dou x. Okay, fine.
Minus.
That's fine here, okay? Now I will close it. Now you will have a minus, and
X.
this minus is already existing inside, huh? So outside minus, you have an outside minus. Okay? So here you will have x outside, then
X dou psi by dou z.
you already have an x, okay? So you will have
X
x dou psi by dou z plus psi
psi. Dou X by dou z.
dou x by dou z. This is it. Now let's get rid of those terms in which the partial derivatives does not match. I mean, you can see this term is gone because it is dou x by dou z. So this I will take across. Okay, this will exist. Okay, this will give me psi, and now let us see what cancels. Okay, let's see that. Okay, what I have here, I have minus zx dou psi by dou x. You check it on your copy,
Minus X dou psi by dou x.
isn't it? This term and this term will go.
Minus
Okay. Now you see here, I have minus x square dou psi by dou z. Yeah, what is here?
minus
This is x square dou psi by, this is minus. Now look at this. Look at this, where I was here. This is its original minus. This minus will be multiplied by the minus that's outside. It will become positive. So you will get rid of it. So you will get rid of this term also. And where am I? Okay. You got rid of this term. Right? So what's the result? The result is this part, psi. Okay? So you can check it yourself. So what we were doing x, ly carrying psi, and we got minus ih bar carrying psi. Now I will remove this psi. So what you get, x, ly will lead us to minus. It is not minus, it is plus. Because there inside it's minus, that minus will be multiplied to minus ih, so it will become minus ih bar. Clear? You got it? Right? Okay. So in the similar way, you can go with YLZ. You can go with ZLX. So for that, what you will have, what you need, so I think I would like to write down them again. So you have LX operator as minus IH bar, Y dou by dou Z minus Z dou by dou Y. This is your LX operator. And then you have LY, that's minus IH bar. This is Z dou by dou X minus X dou by dou Z. and then you have LZ, that is minus IH bar this is X, Y, and Z. So here you have X, dou by dou Y minus Y, dou by dou X. Okay, so you can obtain different commutations between a different position and a different angular momentum. But one thing is clear, that if you have same position and same angular momentum, they are exactly commuting. You can exactly measure the x component of angular momentum and the x component, right? But that's not the case when you take the alternative coordinates between angular momentum and position. So shall we stop here? Any questions? No? Then come on. You just end it. Come on.